Good morning, everybody. It's actually a great honor to have been invited to deliver this series of lectures, which are named after such a remarkable scientist. And I'm very grateful to ICTS and to Spenta Bradia for this invitation. And I'm also especially grateful to the organizers of this whole event who have built a whole discussion session and school around this occasion. So I'd like to name Tanushree, Sahadas Gupta, Indra Das Gupta, Manish Jain, Kedar Damla, and of course my longtime friend, Professor Hulikal Krishnamurti, for extending to me this invitation and especially for organizing this whole thing. I'm also quite grateful to all the friends and colleagues from abroad who came to, for this occasion to participate in both the discussion session and the school. It's a great honor for me to see that the work that was done more than 20 years ago is having some influence still today and is not yet completely forgotten. So it's good to see that there is transmission to a younger generation of students. And this also brings me, last but not least, to thank all the students who are following the lectures. It's actually very impressive, especially for us academics, members of the Western world, to see how knowledge hungry the students of this country are. You have a lot of talent and a lot of desire to actually thrive and learn and succeed in science. And for us, it's an extremely rewarding experience to lecture under such circumstances. So, thank you. I have been instructed to give this first lecture in a kind of almost general audience style. So I would like to warn the experts that this is not at all going to be a technical talk. So you can see it as a recreational activity if you want. The two forthcoming lectures, the one on tomorrow and the one on Monday, will be more, I would say, professional and research-oriented lectures. Okay, so I would like to emphasize that it all starts with materials, you know. Materials have been extremely important since antiquity for the development of civilization, to the extent that entire periods of civilizations are named after a key material. So we can go back in history. I could even have had the Stone Age here, but I chose to start with the Bronze Age. And it's remarkable to see how quite extended periods of civilizations can be named after a certain class of materials that shapes technology, that shapes what mankind is able to do at a certain period of time. So we have the Bronze Age, and now we have entered for already quite a few decades something called the Silicon Age. I don't know exactly when this is going to end, but as you know from this famous curve, it looks like this is not going to end anytime soon, especially here in Bangalore, where IT is so important. Perhaps we have started to enter another age, which is maybe the DNA age, which happily coincides and perhaps even synergizes with the Silicon Age. But let's see how this takes us into the 21st century. Okay, so within this beautiful world of material, we have a playground, and this playground is really the periodic table. The periodic table is a finite set of elements, finite but already quite large. However, the real game starts when one starts assembling these elements into structures. And on the next slide here, I give you some vision of such structures. Here on the left, you see very simple ones. All these structures here are based on a single atom of this periodic table, namely carbon. And you will have recognized here the famous graphene sheet, which, when stacked in this direction, can be made into graphite. Well, that's a modern way to present it. I guess the standard previous way was to talk about graphite and to mention that perhaps one could extract graphene from this, but this is now a reality. One can fold this graphene sheet onto itself to form nanotubes or form giant molecules, which were first actually discovered in the interstellar space, the famous fullerenes. So these are very, very simple structures, very beautiful one also from a single element, but even more complex game come when we start combining several elements of this periodic table into more complex structures. And here, of course, is one famous example of one of these superconducting copper oxides, which has 3 elements and even 4 when you start doping it. So you see that when you start combining many elements of the periodic table, the number of combinations and hence the number of functionalities that you can generate becomes really humongous. And as a side remark, I would like to emphasize that just on this slide, there are actually 3 Nobel Prizes and 1 Kavli Prize. So Nobel Prize was given to graphene, was given to fullerenes, chemistry, was given to high temperature copper oxide superconductor, and the Kavli Prize for nanoscience went to Ijima for carbon nanotubes. So you see how important to both science, technology, and civilization the invention of new materials really is. Okay, so what I would like to emphasize is that very much as in high energy physics actually, these fields cover an enormous amount of length, energy, and time scales. And this, of course, becomes obvious if you think that the characteristic distance, let's say, just at the atomic level, I'm not going to go at smaller scales, but at the atomic level is something like an angstrom, 10 to the minus 10 meters, while when we do experiments, we typically have samples which are millimeter size, let's say, 10 to the minus 3 meters. So you see that one has to cover a range of length scales which is at least 7 orders of magnitude. And as all physicists know, length scales also correspond to time scales and energy scales. So correspondingly, at these very short length scales, we have very high energy scales, which are typically at the atomic scale about 10 electron volt or 10 to the 5 degrees Kelvin, while the energy scales that were actually involved in an experiment at the macro scale are way, way smaller than that. And you find again these 7 order of magnitudes, a typical energy scale that we may want to study in the lab, maybe as low as a few milli-degrees Kelvin. So we could go with the same thing with times. An experiment in the lab in Conuns Metaphysics will last for minutes, while typical time scales at the atomic scale would be more like a femtoseconds, 10 to the minus 15 seconds. So we have to span all these orders of magnitude, and of course, we correspondingly have to deal with enormously collective systems. If you think that a sample of a millimeter cube of matter contains 10 to the 7 to the 3 atoms, which is about 10 to the 21, you will realize that the number of atoms in a very small grain of matter is about the same number than the whole number of stars in the whole universe. So we really have to build a physics of collective systems to deal with this kind of field in physics. And what we have learned all over these years, and here I quote a very famous paper by Nobel laureate Phil Anderson, who was my postdoc advisor many years ago, we have learned from this that more is different. when we go from the micro to the macro scale, we really have emergent properties which we would not be able to read off in the microscopic nature of the constituents, the individual constituents. So Conuns Metaphysics is really the science which aims at understanding at the macro scales the physical properties and the functionalities that emerge from a collective system with its chemical constituents and its organization. Okay. There are many different questions we may want to ask depending on the scale at which we look at the system. We can look at the system directly at the macro scale, or we can start at the atomic scale and make our way up to the macro scale. And the questions we are going to ask when we do these things are not quite the same. If we look at large length scales, at the macro scale, we are going to ask questions like, which physical state is the system in? Which, when you think about it, really means, how does it respond to a small perturbation? How do I know that this is a solid and inside this bottle is a liquid? Well, I basically do this and hurt myself. So I'm applying a small perturbation. More seriously, if we want to decide whether a system is a metal or an insulator, I'm going to apply a small electric field. If a current appears, I will say this is a metal. If not, I would say this is an insulator. So these kinds of questions probe the nature of the system at rest, what we call the ground state, but even more importantly, it actually probes the nature of the low energy excited states. So these are typically the questions we ask when we look at the system at the macro scale. And there is, of course, a very long history in Conuns Metaphysics, one of the prominent figures being Lev Landau, who has taught us that looking at the system at the macro scale is really something that is very universal and very important to do. So this is the kind of question we may want to ask at the macro scale. These are examples of two materials which have exactly the same constituents, just carbon. One, diamond, is hard, it's transparent, it's insulating. The other one, graphite, despite the fact that it only has carbon 2, is brittle, it's black with a little bit of a shiny aspect, and it's almost metallic. The other kind of questions we may want to ask is when we start from the atomic scale. And then we would discover that the only thing that distinguishes diamond and graphite is actually the way the carbon atoms are arranged in the crystal lattice. Here they form this so-called three-dimensional diamond lattice. Here they form these weakly stacked two-dimensional honeycomb systems. And the program that we would have in front of us, starting from the microscale, is really to explain why this only difference between the structural arrangements of these atoms provide these so different properties at the macro scale. So what are these questions good for? Answering the first kind of questions, the ones directly at the macro scale, allow us to characterize and classify the different states of matter, finding that seemingly very different materials, for example, copper and aluminum, actually share very similar properties, and defining a universality class that characterize these universal properties. However, this does not necessarily give us a way to act on the materials or to find new materials. To do that, we need to ask the second kind of questions, namely, how can we infer the function from the microscopic constituents? And only when we are able to do that, we can control and design new materials, which is so important for technology and civilization. So Dirac, in 1929, in a very famous paper that can be considered somehow as the birth of the science of strong correlation physics, wrote a very optimistic and beautiful sentence saying that basically in 1929, all the beautiful edifice of quantum mechanics had been elaborated. All the underlying fundamental physical laws necessary for the mathematical theory, he wrote, of a large part of physics and the whole of chemistry, you see how ambitious this is, are thus completely known. But the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. What Dirac really meant, and this is the only equation of this talk, or perhaps there is perhaps another one later, the only two equations of this talk, is the following thing, is that there is actually one same equation that rules all materials, from diamond to DNA and even more complex organisms, which is the Schrodinger equation. And the Schrodinger equation contains kinetic energy of the electrons and the ions, and it contains interaction, which goes back to the law of Coulomb many centuries ago, which tells us that nuclei interact together with electrostatic forces, and electrons interact with the nuclei with an attractive force, while electrons also interact together with the Coulomb law. So if we have the Schrodinger equation and we know the Coulomb force, in principle, we should be able to deduce everything about the system. When you look more carefully at this equation, you will realize very quickly that there is an extremely nasty term, and this nasty term is the one here emphasized in red, which is the interaction between electrons. This one is not so bad because we can actually consider most of the time the ions of the nuclei to be fixed. However, electrons move fast over femtosecond time scales. We cannot do this for electrons, and we have to face this problem of solving a wave equation for a wave function which depends on 10 to the 21 coordinates, which is not only impossible, but also impossible to even store on any reasonable memory stick. So that sounds a little bit like a reductionist joke in a certain way. You can read here these jokes. I don't know if physicists think they are gods, but certainly when we start talking about solving the Schrodinger equation and deducing the property of DNA, we do behave as if we were something like gods. However, Dirac knew better. If you read this article, you will realize that this sentence was not at all an arrogant sentence about the fact that physicists are God and have discovered the fundamental principles and will leave to engineers and technicians all the rest. He was fully aware that there was a big challenge there, and the next sentence says that it therefore becomes desirable that approximate practical methods, I'm underlining, not Dirac, of applying quantum mechanics should be developed, which can lead to an explanation, and that's very important, of the main features of complex atomic systems, let's say lanthanum copper oxide, without too much computation. So I would like to emphasize that what Dirac meant in 1929 by without too much computation probably meant filling in a few notebooks with his incredible technical talent. What it means today is actually quite a bit different, because in between the computer was invented. But still, this program, Dirac's program, is still very far from being fully implemented and is very much on our agenda at the beginning of the 21st century. I cannot resist at this stage to mention that highly distinguished scientists like Subramanian Chandrasekhar were well aware of this problem. And in fact, I learned here from Vijay Shenoy, I'm ashamed to say that I didn't know that before, that in his pioneering studies of stellar atmospheres, Chandrasekhar had to face the problem of estimating the ground state energy of the H- ion, which is one of the simplest problems in strong correlation science because it has two interacting electrons and a nucleus. So it's the three-body quantum mechanical problem. And he introduced in 1944 a very simple but correlated wave function to describe this bound ground state. Okay, so as I hinted at in the previous slide, this field of physics has been revolutionized since about now 60 years by the emergence of the computer. And I personally believe that numerical physics, computational physics, is an extremely important field, provided the computer is used in an intelligent manner. So many people often have a picture of computational physics as basically a number crunching operation in which you put the physical laws on your computer, you go take a coffee, come back, and read off what the computer wants to tell you. Eugene Wigner used to say, with his beautiful Eastern European accent, it is nice that your computer can understand this problem, but I would like to understand it a little bit myself too. So computational physics is not a number crunching operation. It's a way to actually assist your brain with a very powerful computing machine, and it should be a dialogue between our concepts and what's coming out of clever algorithms suitably implemented on the computer. And I could give a different lecture in which I would show that many, many new discoveries have emerged from this sort of physics that needs to be developed even more. Okay, despite all this laudatio for computers, it's fair to say that interacting fermion systems, even today, are still very hard problems. And I want to spend one slide to explain why this is so. I already mentioned that the number of particles we have to deal with is humongous, 10 to the 21 if we want to be realistic, but let's imagine we even just have 100 of them. The Hilbert space, the space of states of these particles, is exponentially large in the number of particles. Even if these particles had only two states, we would have 2 to the n size of the Hilbert space. So when n is 100, this is very, very large. When n is 10 to the 21, I don't even want to think about it. So diagonalizing fully the Hamiltonian is completely out of the question. No machine can do that, even for a relatively small number of electrons. Fortunately, there are other clever algorithms that can be used. And for bosonic particles, these clever algorithms, which were borne out in the 50s in this very seminal and beautiful paper by Metropolis and co-workers, is called Monte Carlo methods, and then Quantum Monte Carlo methods. For bosonic systems, these algorithms work beautifully well. One can actually understand a system as large as 100,000 interacting bosons and obtain beautiful agreement with experiments from such computer simulations. However, when it comes to fermions, we have a problem. We have a problem because the sign of the statistical amplitudes that we have to sum in Quantum Monte Carlo method is actually random. And this is because fermions anti-commute and wave functions have to be antisymmetric. And at the end of the day, very quickly, direct brute force Quantum Monte Carlo methods for fermions run into trouble. Even a very, very simple model like this one, which I will come back to in the following, which is called the Hubbard model, which just describes a single species of fermions with up and down spin hopping on the lattice with, let's say, a repulsive interaction. So this is really the simplest toy model of our field, which plays very much the role of the Ising model in the theory of phase transition. Even this problem is far from being fully understood. We understand it fully in one dimension. We understand it fully in the limit of very large dimensions. This is dynamical mean field theory. We understand it only very partially in intermediate dimensions like 2 dimensions. So what we really have to do is a quantum mechanics of large systems. And I'm going to spend a few slides telling the story of how this works when we do not seriously consider this difficult term, this red term, which was the interaction between electrons. This I will go rather quickly because I still believe that many, many people in the room know about that, but I feel I need to do that to set the stage. So of course, the first thing that people did back in the 1930s when elaborated a quantum theory of solids was to go ahead and try to simplify this electron-electron interaction term in such a way that at the end of the day you can bring the problem to individual electrons moving in an effective periodic potential. And this problem is ruled by the laws of quantum mechanics. The laws of quantum mechanics is, of course, what makes this sort of sophisticated devices possible, like solar cells or lasers. But they're also what makes this possible, as you will understand in a few slides. This was taken in Mysore a few days ago. And what you see on this slide is beautiful colors of materials. These colors must result from the organization of the atoms in these materials. How does that happen? Okay, so if you open any physics textbook, the view of a solid that will be given is that of a gas of electrons, which are moving in the periodic potential of ions. So here would be a theorist cartoon of this, where we have a lattice of hydrogen atoms. Each of these atoms has 1 electron. But if we get these atoms close together, we can have electrons hopping from one shell to the other. This happens once in a while, like here. And this will allow, in the end, electrons to delocalize over the whole system. How does this electronic motion take place? In the early days, before quantum mechanics was born, Paul Drude in Germany thought that the electrons collide on the nuclei. But actually, this is not true. Sommerfeld and then very much Felix Bloch emphasized that if you have a perfectly periodic solid, these electrons can actually travel through the whole system like a wave, which is called a Bloch wave. You should really think of this being possible because of a very remarkable quantum mechanical effect that has no classical analog, which is the tunnel effect. In classical mechanics, we cannot go over a hill without climbing it. In quantum mechanics, we can, because particles behave as waves, and waves can go around obstacles. This is the tunnel effect. And what happens here is really that the electrons delocalize from one atom to the next by the tunnel effect. As a result, the collective state of this electron in the field of the ions is really like a giant molecular orbital or a wave which is delocalized over the whole system. However, these Bloch states do not exist at all energies. This is a plot of the energy of these Bloch states as a function of the wave number, which is essentially the inverse of the wavelength of this wave. And you will see that there are regions of energy where these states exist, these Bloch waves exist. This is called an energy band, and other regions of energy in which no such state exists. And you could describe this as a gap between two energy bands. There are no quantum states available there. Once Felix Bloch and others had realized that in the early 30s, the distinction between metals and conventional insulators became obvious. What we have to do if we view the electrons are essentially independent, if we neglect this red term, is we just have to fill these individual energy levels by electrons, remembering that they are fermions and have to obey the Pauli principle, So we can only put one electron with spin up and one electron with spin down in any of these block waves. This results in the fact that depending on the counting of electrons and the structure of these block waves, we can end up in a situation where the maximum energy of occupied states lies in the middle of a permitted band, or in a situation where the maximum energy would lie in the gap. In such a situation like this, we can easily excite some small excitations, so we would have a metal. In a situation like this, we cannot, and we would have an insulator. So you see that you need the power of quantum mechanics, you need the tunneling effect, and you need the Pauli principle to understand why certain materials are insulating and why others are metallic, and also to understand why certain materials are red while others are black or transparent. The explanation now is very simple. If we shine light on a piece of insulator, if we have an energy gap that is smaller than the lower edge of the visible spectrum, which is about 1.8 electron volts, then all the radiation of the sun is absorbed in the material and it will look like black. If we have a gap which is very large, like in diamond, all the light is transmitted and the material is transparent, like diamond. But if the gap lies somewhere inside the visible range, we would have a colored insulator, and that explains what we see on the Mysore market. This also explains why this pigment is actually red, because it's an insulator with a gap which is about 2.1 eV. So all the red light goes to your eye, and all the rest is absorbed in the material. This pigment is called vermilion, or I'm told sindoor in this country. Even though if you look at the Google, there is a controversy. So sindoor is a very famous pigment in India because it's this red thing that married women especially wear. And there is a controversy on Google whether sindoor is actually mercury sulfide, which is vermilion, or whether it's a lead oxide. So I will leave it to you to decide. This controversy, the poll is about 50%, 50%. I didn't have time to sort it out. Whether it's mercury or whether it's lead, one thing is clear, is that they are both toxic. And one of the material design enterprise is actually to find new such pigments. And in fact, the French company now called Rhodia about 10 years ago, developed a non-toxic alternative to these red pigments, which is this time a cerium sulfide, which doesn't do anything too bad to your body. And believe it or not, it's actually a Mott insulator rather than a conventional insulator. So Mott insulators are good for your health. Okay. So we're about halfway through the lecture, and what we have learned is that it's really the individual motions of electrons in the periodic potential in quantum mechanics, plus the statistical correlations from the Pauli principle and the Fermi-Dirac statistics, if you want, which is responsible for the basic distinction between metals and conventional insulators. So this is a beautiful page in the history of physics that covers many decades, but as you can probably guess, I'm going to be mostly interested, and we are interested in this discussion session and school, in situations where these sort of descriptions do not work. So this is what I really want to explain now. Failure of this textbook picture. The physical phenomenon that best emphasizes this failure is the so-called Mott phenomenon. What is the Mott phenomenon? Here you see the same cartoon of electrons trying to hop by the tunnel effect from one hydrogen atom to the next. They try to hop, but when they try to do so, this famous red term that we had neglected, which is the electron-electron interaction, tells them that it's very energetically unfavorable to do that. And you immediately guess that there is a competition of energy scale. If the typical scale, which we call U in our community, for this repulsive interaction is smaller than the amplitude for the tunnel effect, yes, perhaps we are going to have a metal. The Pauli principle, since we only have one electron per site, allows that. But if this U is larger than the tunnel amplitude, then the motion is blocked by the repulsive interaction, and we have an insulator. But this insulator is not a conventional insulator a la Felix Bloch. It's an insulator which is insulating because of strong repulsive interactions. We call this a Mod insulator after Sir Neville Mod. In fact, a Mod insulator is the simplest kind of insulator you can think of. It's really an incompressible state of matter, which is incompressible because you cannot decently add another particle without paying a very strong repulsive interactions. In Bangalore, you are very familiar with this. We are also very familiar with this in Paris. In Paris, we have other kinds of incompressible fluids, like this one. When your subway is going to be completed in a few months, or I think, you'll also get to know this. As I said, a Mott insulator is the simplest kind of insulator. As Groucho Marx would say, a child of 5 would understand a Mott insulator. Send someone to fetch a child of 5. Okay, so this is the science we are interested in. It's the science of electrons when they behave in a strongly interdependent manner, not just because of the statistical correlations of the Pauli principle, but because of interactions. In our jargon, we call these materials materials with strong electron correlations. I want to emphasize at this stage that the Mott phenomenon at strong coupling has nothing to do with magnetism. This is often a confusion, even by practitioners of the field. It has nothing to do with spin correlation. It is due entirely to the blocking of density of charge fluctuations. The system is basically an insulator even way above any magnetic ordering temperature. Okay, so I mentioned to you that we have these complex materials, but we also have very simple toy models like this one, which still resist full understanding. And you can ask, you know, is this toy model really relevant to any physics? And the answer I would have given you 20 years ago or now would be very different. We now know how to realize in the laboratory actual systems, which I would call artificial materials, which are precise realizations of this model. And this is done by bringing together two different fields, the field of Conuns Metaphysics and the field of quantum optics. We can realize in the lab, not me, but my talented experimental colleagues, ultra-cold atomic gases in optical lattices, which are really incarnations of these simple toy models. How is this done? This is done with completely different things than electrons. It's done with atomic vapors that are brought to very, very, very low temperature, actually the lowest temperature known in universe, on the order of nanokelvin, way, way, way lower than the primordial background radiation temperature, which is very hot, 3 Kelvin, you know. This is 9 orders of magnitude smaller. And what you can do, you have these very cold atomic vapors, and what you can do is you can actually trap these atoms with laser beams into structures that look like this egg box here, so that you really realize artificial crystals of atoms and lights. If you think of my real materials, what plays the role of electrons here are these atoms, while what plays the role of the periodic potential of the fixed ions are the laser beam, the potential created by the laser beam. And this is another beautiful playground that has been made possible thanks to the work of these people in particular, Steve Chu, who has been on the political scene after his scientific oops. Time machine doesn't want to complete my backup, but I don't really care. Interesting. Here we go. Yes, so thanks to the work of these people, Chu, Tanucci, and Phillips, who actually received the Nobel Prize for this, we know how to cool these atomic vapors to such very low temperatures. And we also know how to realize collective states of quantum fluids of these particles. This is another Nobel Prize given for the Bose-Einstein condensation of these atomic vapors. And a new field has been emerging thanks to these developments, which is really the field of Conuns Metaphysics with ultra-cold atoms. These have great beauties because they are highly controllable systems. The interaction strength, the U of that toy model, can be tuned by just changing a magnetic field or the depth of the lattice using the so-called Feshbach resonance method. Hopping can also be tuned by changing the lattice depth or the laser intensity. The geometry of the lattice can be engineered at will. There are no impurities, there are no phonons. So these are really sort of analog realization in artificial materials of the complicated toy models that we are interested in our field. One of the beautiful experimental demonstrations that was done about 10 years ago in this field is precisely to show that if we control these parameters, we can induce the phase transition between the superfluid state of bosons and a Mott insulating state of bosons. So Sir Neville Mod comes into quantum optics. This is the experiment. It was done by Markus Greiner, Tilman Esslinger, Emanuel Bloch at that time in Munich. And what you see here is the interference pattern resulting from all the individual condensate in the different wells of the lattice. As you crank up the depth of the periodic potential, you see here that there is a beautiful Bose-Einstein condensate, and here that it's completely gone. So you interpret this by having gone from a superfluid to a Mott insulator. Similar things have been done more recently for fermions. I'm not going to detail this now, but what I want to advertise is that in my third lecture on Monday, I will talk a little bit, well, I will devote, in fact, the whole lecture to this field, especially showing how we can now study transport phenomena in these ultra-cold atomic systems, which brings together the field of the mesoscopic transport in small systems, in electronic systems, with the field of cold atom, and I will particularly show you how one can measure not only the conductance of such devices, but also reveal thermoelectric effects in such systems. But let's now go back to materials, to the materials of the chemist with strong correlations. I've mentioned the existence of such materials, but I haven't told you who are the suspects, what they are really. Well, the suspects are materials in which the orbitals in which the electron lives are fairly well localized around nuclei. And you can guess why this is the case. This is the case because if these orbitals are reasonably well localized, the tunnel amplitude between different atoms will be small. And also, the matrix element of the Coulomb interaction will be fairly large because there will be relatively limited screening. So we will go into regimes where the matrix element U can be significantly larger than the individual hopping matrix element and will reach this strongly correlated regime. Where do we find that? Well, let's go back to our favorite playground. We find that when we look in the periodic table at the series of so-called transition metals, which corresponds to the gradual filling of the 3D shell, and to some extent also 4D or 5D shell, and especially when we fill in the 4F or 5F shell, and Didi Sarma in his talk in the school actually beautifully explained why these materials built on these elements have competition between localization and delocalization. So the thing I would like to emphasize is that because of the interdependence of these electrons, materials with strong electronic correlations do actually big things. In the morning, we had two talks which were focusing on methodology, and for this purpose, picked materials, strontium VO3, which is actually a kind of Drosophila, which doesn't do too much. But and this is very legitimate to do, because this is a material on which you want to test methods. But the reason we are interested in this field is that, by and large, most of the materials in this class of strongly correlated materials do remarkable things. They have collective phenomena of great diversity and with very large amplitudes. So what are these collective phenomena? There are two very prominent ones, magnetism and superconductivity, and also metal-insulator transitions. And the thing which is important is that these materials can be very easily switched, in fact, too easily switched from a certain point of view between these different states, because these different states differ in energy by small amounts. So we have a diversity of different phases with small energy difference, and the phases competing with one another. Let me give you some examples. This is a system, a vanadium oxide, that has a series of metal insulator transitions. And when you actually cool down, this paramagnetic insulator actually orders into an antiferromagnetic insulator, so you have magnetism. So you see that by tuning a simple parameter like pressure, you can actually switch between these different phases. This sort of phenomena is not only interesting from a fundamental point of view, but is also potentially interesting for applications. And this is an example of another vanadium oxide, vanadium dioxide, which has the good taste of having a metal insulator transition at a temperature which is very close to room temperature. At high temperature, it's a metal, above about 20 Celsius. At low temperature, it's an insulator. So you can actually use this to coat windows and climate control your room. This is actually something that is, in fact, fabricated by companies like Saint-Gobain in France. At high temperature, when it's warm outside, this material will reflect in the infrared, so you will avoid your room to heat too much, while at low temperature, you will let in the warm sunlight into your room. It's not so intelligent, windows, but for a window, it's kind of an intelligent behavior. Okay. Of course, there are much more spectacular examples. One of the most famous ones, which really rejuvenated this field in the mid-80s, is the discovery of a new class of superconductors that I already mentioned, which are the copper oxides, which completely changed our appreciation of superconductivity by boosting Tc from the 20 Kelvin range to very high temperature, not yet room temperature, but let's say a factor of 2 from that. So material science, to a large extent, has to do with factors of 2. If we could increase Tc by a factor of 2, this would, of course, bring a technological revolution. If we could increase the so-called figure of merit of thermoelectric materials by a factor of 2, this will actually revolutionize completely the refrigeration industry. You will replace all your fridges by solid-state fridges, and so on. This factor of 2 hides a lot of fundamental issues that need to be understood to be able to overcome it. Okay, copper oxide superconductors are not only promising from the point of view of perhaps one day reaching room temperature superconductors, but they're also very interesting from a fundamental point of view. They are really a headache for theorists, and the people who in this room who are working on that know what I'm talking about. They have a very rich phase diagram, so again, this competition between different phases from which you can switch by small perturbation. But they have also regimes like this metallic regime here, in which the textbook picture of elementary excitations in metals just fails. This is illustrated here a little bit later in the talk, where one shows, where I will show that quasi-particles in the conventional sense do not really exist there. Okay, another example of a material that can be switched between different phases are these manganite oxides, where you can have very, very strong dependence of the resistance on magnetic field with, again, possible future applications. Okay, so you've understood at this stage already, or you felt that these strong electronic correlations really force us to reconsider fundamental descriptions of the solid states. These electrons hesitate between iterant and localized behavior. In fact, they are localized on short time scales, and in metallic systems, they manage to delocalize on long time scales, But the question is how to actually describe this. Since the beautiful theory of this person here, Lev Landau, we have come to appreciate that in many metals with interactions, the actual elementary excitations, which are so important to understand the response of the system to weak perturbation, are actually very similar to electrons. They are electrons dressed by interactions. This is called quasi-particles, and you can view it as an electron traveling through the system and dressed by a whole cloud of excitation, so that it will have a slightly different, or perhaps a very different effective mass, but still will behave as an individual electron. These quasi-particles can be detected by beautiful spectroscopic techniques, which Atsushi is a pioneer of, so-called photoemission spectroscopy. And when there is such an excitation, you see it as a peak in this photoemission spectrum. Now look at what copper oxide superconductors do. This is measuring the photoemission spectrum of a copper oxide metal, going from the so-called nodal position on the Fermi surface to the so-called antinodal position close to the boundary of the Brillouin zone. And you see that these materials are particularly perverse, because what they do is that they have a sharp quasi-particle peak there, but they have no quasi-particle peak at all there. So it's not only that Landau theory of conventional quasi-particle excitation fails, it fails in a way which is momentum selective. It fails badly here, but it kind of survives there. That is the problem. This is one of the most perverse problems that is brought to us by these materials. So in order to deal with these systems, and in order to deal with this competition between localized excitation on short time scales and itinerant excitations on long time scales, we need to change our textbook picture. We need to think in terms of atoms and not in terms of an electron gas. This is not a big surprise for a chemist, but this is kind of a different way of thinking about the solid state for conventional Conuns metaphysicists who have been trained to thinking that solids are just an electron gas with perhaps some annoying interactions on top of them. So this is precisely what this theory that was referred to in several instances previously in the school and in the talks in this morning, but not yet really explained, has aimed at doing. This so-called dynamical mean field theory emerged initially as attention paid to the limit of the Hubbard model in large dimensionalities, which eventually resulted into the construction of a mean field theory of the strongly correlated system that Gabi Kotlia and myself elaborated in the early 90s, and which is now known as dynamical mean field theory. I will devote lecture 2 of the Chandrasekhar lectures to briefly introduce this theory and especially give you some overview of the most recent results that have been obtained with this theory. So I will not spend a long time now, but just to give you a flavor, the idea of this theory is instead of dealing with this very, very complicated problem of 10 to the 21 atoms with all these electrons interacting together, we actually replace this problem by one atom, not one electron, one atom, which is a small many-body problem in itself with all its internal correlations, hybridized with an effective medium, which is, of course, representing the rest of the system with which this atom can exchange electrons. This kind of approach is conceptually a very direct extension of the mean field concept in classical statistical mechanics to quantum many-body systems. However, instead of a single static Weiss field, you have to describe the history of these exchanges. So it becomes really an effective time-dependent action, which is describing the system. Okay. So if you want to learn more about dynamical mean field theory, you can come to my second lecture, which will be tomorrow morning, in which I will say a bit more about the method and especially emphasize some recent developments about the physics of these materials that this method has allowed to reach. And the entire school that has been set up here is, of course, devoted to the happy marriage between dynamical mean field theory and first principle electronic structure theory of real materials, something that has happened since the late 90s until now, which now allow to have a precise computational framework to calculate the properties of such materials in the presence of strong coalitions. Okay, so I will use the last 5 minutes of this talk to emphasize some new direction. Up to now, I have described the functionalities of these materials. I have emphasized that there are many different competing states and that the system has this tendency to switch between these different states with small perturbation. I have also emphasized the fundamental issues that these systems raise, but I have not talked about a direction which is perhaps the most important one, which is how can we actually control this material? How can we actually teach them to do what we want rather than be stuck in front of nature and try to understand what nature does? So this is, I think, a new direction in this field that has started a few years ago. And I would like to emphasize that one can now explore this possibility of controlling the electronic properties of correlated electron materials via selective control of their structure. And I would like to emphasize the word selective here. There are many people who have been working on this. As far as I am concerned, this is an emerging research direction, in particular through this IARC synergy grant that I've been obtaining recently in collaboration with Andrea Cavalieri, who is the leading PI in this operation, Dieter Jaksch, which brings the quantum optics aspects of all this, and Jean-Marc Triscon in Geneva. So the idea behind this is to exploit the phase competition on similar energy scales that I have repeatedly emphasized to our advantage. This competition comes from the fact that we have two different states of the system, and the energy difference between these two states is quite small, so that small perturbations can switch from one phase to the other. This is often a complication because this phase diagram as a result have many, many different phases. But perhaps if we can control and trigger the material to sit there when actually in real life, in equilibrium life, you would like to sit here, we can perhaps exploit the functionality of this state, which may be more interesting than this one. So this is the idea. How can we do that? We can do that by at least two different routes. One has been already quite a bit explored in the last 10 years, and the other one is an emerging direction. The first route is to build artificial materials by either growing these oxides on a substrate which is carefully chosen so as to induce a strain or a structural constraint in the oxide you are interested in. So this is the whole field of strain films and heterostructure of oxides. Another route, which has been really pioneered by Andrea Cavalieri in particular, is to do selective excitation, selective control of the structure with dedicated lasers which can excite specific structural modes in a resonant manner. So let me elaborate a little bit more on these two directions. Using techniques for growing materials like molecular beam epitaxy, one can actually grow these oxides layer by layer, forming materials that do not exist in nature, but that are nevertheless perfectly stable, in which we can combine the functionalities of different oxides and induce interfacial strains and so on. This has led to, for example, to the discovery of superconductivity in lanthanum aluminum oxide, strontium titanium oxide, interfaces in which you combine two insulators and find an electron gas at the boundary, which is a superconductor. You can do that. You can strain the system in thin films, and so on. The second route is this selective control with resonant light. What is the idea there? The idea is to use a laser pump which is able to excite some specific structural mode. For example, take a copper oxide and shake the copper oxygen octahedron like this, which these people know how to do with their lasers. And what one finds is that this triggers a structural change of the whole system into a transient new phase, which will have a different physical properties. Of course, when you remove the laser light, you go back, possibly, to the previous state, but you could imagine pumping the system continuously to induce a new physical property. There's been already quite spectacular effects that have been demonstrated with this technique. I mentioned these manganites, which have competing states on similar energies, and it has been shown a few years ago in this beautiful paper by Rini et al., that you can actually, by shaking these octahedra in this way, induce a transition between the insulating state of this manganite and a metallic state of this manganite, which would not nominally exist at equilibrium for this chemical composition. How does that work? This is due to the nonlinear coupling between the phonon mode you are exciting and another phonon mode, which is not light sensitive, which is not dipolar active, but which is nonlinearly coupled to this pumped infrared active mode. This was conjectured in this beautiful paper by first Cavalieri et al. And recently, we came up with a very, very bright postdoc of ours, Alaska Subedi, to a microscopic theory in which we can actually computationally predict how the structure will change when we pump a specific infrared active structural mode. Recently, Andrea has been doing some very beautiful works experimentally in which they demonstrate that by pumping, doing similar pumping techniques or resonant excitation techniques in cuprates, they can actually trigger this material to have transient superconductivity at room temperature. So we have the hope that by better understanding this, the physics behind this, one can actually use the structural selective control to our advantage and generate some electronic functionality that would be interesting. Okay, so this is the end of my talk. I will just conclude with this general slide. I hope that I have convinced you that this sort of material science, and in fact material science in general, constantly feeds us with novel questions which have both a fundamental side. For example, how can quasi-particle excitations disappear? What are they replaced by? But also a design and control side. So you do not need to be trapped into this wrong view that there is fundamental science and there is applied challenges. In fact, it's a two-dimensional space. You can very well live here where you will happily take your inspiration from applied challenges and be confronted with the fundamental issues, perhaps the very fundamental issues that are raised by the science of these collective systems. And this kind of point of view has been developed in this beautiful book, which takes Pasteur as an example, as a glorious example of somebody who actually took inspiration from very concrete problems. We could also quote De Gennes, who was in the similar vein, and brought this in the field of fundamental science. Thank you for your attention.
Are there any questions, comments? We have a little bit of time.
The students should not be shy.
I think if you take certain molecules, I don't know the solid state equivalent, like azobenzene, which has two quite stable states because of the light interaction, then
Yes.
it, is it possible that you might get not the transient change, but probably more permanent? So
Yes,
are there
in fact, of course, the field of femtosecond chemistry is a very well-established field that has existed for a few decades already, that led to the Nobel Prize of Ahmed Zivai, in which the hope, the agenda is to control chemical reaction by suitably designed femtosecond lasers. You can view this to a certain extent as the challenge of doing similar things in the solid state. But here in the solid state, we have this possibility of really tuning our pump to specific modes in a resonant manner and inducing a collective phenomenon. So your question, if I hear it correctly, is how can interaction be controlled?
Yes.
Yeah, that's a very, very good question, because naively, you would think that you have an atomic vapor. First of all, this vapor is very dilute, so how can it have strong interactions, right? And also, how can you control that? Because the scattering length is what it is, right? Okay, so in fact, this is not so. There are two things that allow you to control the interaction. The first thing is that the scattering length can be changed even in the gas without optical lattice, okay, can be changed using the so-called Feshbach resonance mechanism. What is the Feshbach resonance mechanism? You have some states of your atoms, okay, and if you change the magnetic field, which will act on the different hyperfine states of your atom, you can promote a state from being a bound state to the continuum, right? You can kick out a state from the bound states to the continuum. And when this happens, the scattering length of the other states have a divergence. So you can actually reach a value of the scattering length which is very large, despite the fact that the gas is very dilute. And you can control the value of the scattering length by the tuning of magnetic field. So this is how to control interaction in the gas. Now, when you put this gas in an optical lattice, you have an additional knob, which is the depth of the lattice. The interaction strength, the U now, is really a matrix element of this contact interaction into localized Vanier functions that the students of the school have learned about of the optical lattice. And if you have a very deep optical lattice, these Vanier functions will be very localized, so that this matrix, so concentrated on a site, and this matrix element will be very big. So in fact, in the optical lattice, you really have two knobs to tune your interaction, which is the depth of the lattice and the Feshbach resonance. And the depth of the lattice also controls the bandwidth, so the kinetic energy term. So you really can control both.